All right, welcome back. So I hope everyone made it through the important stuff in the last video. I get it if you skipped the introduction, the objectives, all that stuff, but it's really important to understand the difference between a binary heap and a binary search tree. They look similar, but they are different. So here we have a max binary heap. 41 is the root. The two children need to be smaller. That's really the only rule. Also notice that we fill in the left first. So I mentioned that in the last video. The left child is added and then a right child. And then if we were to add a right one here, the next child would be added to the left down here. So we'll come back to that when we actually implement this. So suppose we wanted to represent this, we want to basically write code to model this, just like we've done with every other data structure. We could implement a tree class and a node class, and each node has a left and a right. And we could do the same thing we did for a binary search tree, but there's actually an easier way. So we can actually use a built-in data structure, an array or a list, same thing, just different names in different programming languages. We can use that to store a binary heap, and I'll show you how. Okay, so there's a little tiny bit of math involved here, not much, just a little multiplication and addition. But if we look at this binary heap, so this is a max binary heap again. We have 100 up top, the largest value, and then below it, we just have two values that are smaller than 100. So again, we don't have the two next largest numbers. It's just two numbers that are smaller, 19 and 36. And then they both have two children. It's kind of hard to see in this diagram, but if we were to actually expand it vertically, we wouldn't have any space left to show this. So this down here is our array or our list where we're storing values. It's indexed. So we would have 0, 1, 2, 3, and so on. So we put 100, we put the root at the first index of 0. Here we go. I added in the indices down here. And then what we can see, let's say we want to find the children of 100. Well, we know where they are. It's the next two values. The left child is 19. The right child is 36. So we have index of 0. Its children are index of 1 and index of 2. All right, well, that part's easy because it's sort of a special case at the beginning. But now if we wanted to look at the children for, let's say, 19, well, we have to skip over 36, right? And if we look at this diagram, 19 has two children, 17 and 12. So the 17 is the left child, and 12 is the right child. So we have a parent at index 1. Its left child is index 3. Its right child is index 4. Okay, next, let's go to 36. So we had 36. We have to leapfrog over to get to 25, which is its left child, and 5, which is its right child. So index of 2 corresponds to two children at index of 5 and 6. Okay, well, I didn't do this for every single value, I promise. We're about to skip ahead. 17, though, its children start at index of 7 for 9 and index of 8 for 15. So can you figure out the little mathematical relationship here? What if you have an index for a parent, where are its two children located? Here's one more. 5 is the parent. Its children are located at index of 13 and 14. So index of 6 was the parent index, not indices, and its left child was 13, its right child was 14. So what's the relationship here? So for any index n inside of an array, the left child is stored at 2n plus 1, and the right child is at 2n plus 2. Okay? So if we take index 6, for example, we find its children by multiplying that by 2 and adding 1. So 6 times 2 gives us 12. We add 1, we get 13. So that's the left child. We add 2, or we add 1 more, really, we get 14. So they're side by side. Or let's take this index 4, the value of 12. Its children, we multiply 4 by 2, gives us 8, we add 1. So that's going to give us 9 and 10. We add 1, we add 2. 6 and 11, is that correct? Yes. If you follow this line, it's hard. 12's children are 6 and 11. So that's the formula to actually find a child based off of a parent. We take the number, the index, n, we multiply by 2, and we add 1 to get the left, we add 2 to get the right. And we'll be doing that in our code. Hopefully the relationship there makes sense, and you can see how that works and why it works. If not, we're going to come back to this, and you can just add this into your code and just assume that it works. But I think if you think about it, there's two children per each node. and we need a way to flatten that and store that. I like this diagram. It just shrinks it all and smushes it into this list, and you can see how it works. As you move further and further down, you have a lot more children. Anyway, so the other thing is we can work backwards. If we have a child node and we want to know its parent. So it's the same exact math relationship, you just go the other direction. So if we have a child of 6 at index of 9, its parent is at index of 4. Or if we have index 12 for the child, we can figure out that its parent is at index of 5. And the math for that, so if we have a child at index n, we subtract 1, divide by 2, and then also we floor it, meaning we just chop off the decimal, because we can't have 0.5 decimals in as far as an index. They're whole integers. So if we go back and say we're working with 13 right here, index 13, the value is 1. To find its parent, we subtract 1, which gives us 12. We divide by 2, gives us 6. So at index 6, we have the value 5, and that indeed is the parent of 1. Let's try one more. How about index of 10? So at 10, we have this value 11. To find its parent, we subtract 1, which gives us 9. Then we divide by 2. Remember, it's n minus 1 divided by 2 floored. So we take 10 minus 1, that's 9, divide by 2, 4.5. Well, there's no index 4.5, but if we floor it, we just chop off that decimal, we get 4 right here. So the value of 12. Is that indeed the parent of 11? Yes, it is. There it is. So that's the math. That floor part is important because we can't have, like I said, we can't have 4.5 as an index. Okay. So those two things we will return back to because there will be situations where we have a parent and we need to find its children, in which case we do 2n plus 1, 2n plus 2. Or if we need to find a parent based off of a child, it's n minus 1 divided by 2 floored.